These are Higher Physics Notes, Unit 1, Section 4, Collisions and Explosions. And this is part 2, where we look at explosions. Well, we can treat explosions a little bit like collisions in that we will have a before situation and an after. The difference is, in an explosion, the body that we have before the explosion already contains a supply of energy. So if you think of a stick of explosives, for example, it's got chemical energy inside it. The explosions we deal with are relatively simple ones, where the original body will split in two into mass M1 and mass M2. Typically before the explosion, the body is at rest. So that's the before situation. What happens is the body can only explode if it already contains some energy. So for example, explosive charges contain chemical energy. And then once that energy is released, the original body breaks up into two or more fragments. Now in a real bomb, of course, there would be thousands of fragments, but in our explosions, we are keeping them really simple. We are imagining only two fragments. You'll be glad to know. Right, there we go. So we've got M1. And M2. Now let's imagine that M1 flies off to the left at velocity v1, and M2 flies off to the right at velocity v2. Now notice they're going in opposite directions to each other. That is required by the law of conservation of momentum, because clearly M1 has momentum to the left, therefore M2 must have momentum to the right, which is equal and opposite to the momentum to the left, because there is zero momentum beforehand. So let's see how this works then. Well, let this fragment be 2 kilograms and this smaller fragment, or lighter fragment at least, be 1 kilogram. And let's imagine that the right hand fragment goes off at 10 meters per second. The question is, at what speed does fragment M1 go off at? Well, we apply the law of conservation of momentum just like we do in collisions. So we begin by saying the total momentum before the explosion must equal the total momentum after. The law of conservation of momentum can never be breached in the absence of external forces. And there aren't any external forces here. All the forces involved originate in the explosive charge and the chemicals within the body itself. So these are internal. Well, before the explosion, there is clearly zero momentum because the body is at rest. And you'll always have the left-hand side being zero in explosions. On the right-hand side, we've got M1v1, the momentum of fragment 1, added as vectors to M2v2, the momentum of body 2. You don't put any signs in until you put in the numbers. Well, in this case then, 0 equals the 2 kilograms times V1 plus the 1 kilogram times the 10. Now we need to use the sign convention. To the right is positive, so I'm regarding the 10 as a positive number. So tidying that up, 2V1 is going to be minus 10. Therefore V1 itself is going to be minus 5 meters per second. Now the negative sign means to the left. And as you can see, mass 1 must indeed go to the left. Therefore, to the left is negative, to the right is positive. So that's why it's got that negative velocity to the left. When you're giving your answers, give the minus sign. So say V1 is minus 5 meters per second, and I would put brackets, i.e. to the left. And that's quite simply how explosions work.